Okay. So of course, we are still in chapter 10, working on hypothesis testing, and we're going to work through this example together. And we're going to do the full, complete, hypothesis test. So I'm just going to add here, complete a full hypothesis test. Okay, so there's no confusion. Remember what I mentioned last week is every time we do a hypothesis test, it's a full hypothesis test, all 5 steps. Okay, so let's just kind of skim through this. I know I always tell you guys don't skim. All right, let's read through this. So red-green color blindness causes problems in distinguishing reds and greens. Many studies have been conducted with Caucasian males, so it's white males, among whom 8% have red-green color blindness. However, there is limited information on this phenomenon among other ethnicities. A researcher in China believes the percentage of red-green color blindness for Asian males is different than the 8% for white males. She conducts a study on 200 randomly selected Asian men and finds that 9 have the red-green color blindness. So complete a full hypothesis test. This gives us all our information we need. You guys, just reading through this problem, I'm thinking it's categorical. The reason why I'm thinking it's categorical is because I'm first kind of ruling out numerical. I don't see anything that says average or the word mean anyplace. When we're talking about the sample doesn't give me X bar or S, so the sample mean or sample standard deviation doesn't give me anything like that, right? It just says 9 out of 200. When I have a 9 out of 200, that makes me think about categorical, right? It's X and N. And then if I'm going back and reading through, it's talking about 8%. Right here, I have a percentage. That to me is categorical. So I'm kind of ruling out why it's not numerical. And then I'm going back and looking and saying, oh yes, it is categorical. I do have this proof that it's categorical. Plus, when you look at the context of the problem, I want to know if someone fits in that category. Do they have red-green color blindness or not? Right? That's category they fit into. That's categorical data. Okay. So let's take a look at the full testing process. So the first step, of course, is my population step. My population step, the first part, I'm going to identify the objects in the population. Remember, this is not always people, but in this case, it actually happens to be. So when I look through this and I want to identify the objects, I'm going to see where the sample is, and I want to get the information from there. So it says she conducts a study on 200 randomly selected Asian men. That's who we're studying, Asian men. So now I can just say over here, it's all. Remember, I always say all and then whoever we're studying. So Asian men. So my objects. All right, and my variable. Remember what a variable is? That is what's changing from individual to individual. So here it's person to person. What's changing from person to person? And that's if they have that red-green color blindness. So I usually word mine as a question. I want you to just keep in mind, you can word it any way you want. I'm going to say, it's kind of vague, but are they red-green colorblind? Kind of keep it short. And I'm going to put a question mark. And of course, I'm going to put that yes, no. That kind of helps me realize, okay, this is categorical. So here I'm going to just put that this is categorical. Remember, I like to see this. I like you to tell me categorical, numerical somewhere is here with the variable. The reason why we do this is because everything after this flows from that, right? So this drives everything else that I'm choosing. So here, my unknown is going to be P because it's categorical. P is the population proportion. Now here, I could always start my statement this way, but now I need to add the context, meaning I need to pull in the objects in the variable here so it has some meaning behind it. So P is the population proportion. I'm going to just say of Asian men who are red-green colorblind. Again, this kind of thing you can word different ways and it has the same meaning. So I want you to keep that in mind. All right, and then I have my goal next. Remember, the goal is to show support, or you can word this different ways as well, show sufficient evidence to support, whatever. To show support for my HA. I'm not gonna fill that in yet because I don't know my HA. So I'm actually going to move down. I'm gonna leave some space and I'm going to start, now I'll actually complete the method step. And for the method step, I have my null hypothesis and my alternative hypothesis. I'm out of room, so I'm just gonna go over here horizontally. Alpha and the T-curve I'm on. Remember, each step has 4 parts except for the conclusion. So I don't ever start with my null, I actually always start with my alternative. So it's what the researcher believes, and it says the researcher believes that it's different than, right here, different than the 8%. So what the researcher is saying, she's not saying anything specific, like if it's greater than or less than, she's just saying she doesn't think it's 8%. She doesn't know if it's higher or lower, she just doesn't think. So here, this is where I have a not equal to, and I'm going to write my 8% as a decimal, 0.08. Now, what do I have to fill in here is my unknown, right? So since it's categorical, it's P. My population proportion is not equal to 8%. Then my null is exactly opposite. P is equal to 0.08. My alpha, you can kind of go different ways here. It's not given to me. I'm going to say it's 5%. Because I really think this could be kind of almost like a medical thing, right? But I don't think it's a life or death situation. So I'm going to go with alpha equals 5%. Remember, on an exam, I will always provide this to you, so you'll have this. But sometimes on these team assignments or problems like this, you know, we kind of work through choosing it. So remember, 1% or 0.01, we kind of save that for life or death situations. And since this is categorical data, we are on the Z-curve, and the Z-curve does not change shape. It stays the same all the time. So I don't need to do anything like degrees of freedom like I do for the T-curve. So now I have this HA. I'm going to go back up to my goal, and I want to write my goal. So it's to show support that P is not equal to 8%. That's what I want to write up here. Well, we've already described P or defined it in words. So I could just copy and paste this and then tack on the end, not equal to 8%. So that's exactly what I'm going to do. So to show support, I usually say, to say that, you can write it however you want, the population proportion of Asian men who are red-green colorblind. Now I can say does not equal, or is not equal to, or it's different than. You can word it so many different ways. I'm going to actually use the wording from the problem and say it's different than. Is different than 8%. So you can write it different ways. If you just say it's not equal to 8%, it means the same thing as different than. So there's my goal. Remember, I have this really nice goal. I'm going to use it in my conclusion, in my last step. Any questions on the first 2 steps here? Okay, so let's take a look at the next few steps. So the next step we're going to look at is the sample step. This is kind of like that quick, easy step for us. when I was grading the team assignments, I don't think I had any corrections on the sample step, which is really nice to see. So in my sample step, it depends what type of data I have, right? So we have categorical data. So I want to identify what X is equal to, what N is equal to, my P hat, which is X divided by N. And I need to check to see if it's normal or normally distributed to see if the Z curve is appropriate. So X is from the problem. I have it here. And this is all my sample step. So right here, where a study of 200 randomly selected Asian men, find that 9 have red-green color blindness. So X is 9. That's the number of people that have the characteristic out of N, which is 200 people that were in the study. So my P hat is 9 divided by 200, which equals 0.045. That's my sample proportion. Now for normality, I have to check to see, there we go, if N times P times 1 minus P is greater than or equal to 10. But remember, it's not P here. We use the center of the curve, which is P naught. So from here, N is 200 and P naught is the center of my curve. The center of my curve comes from my null hypothesis. My null hypothesis here is 0.08. So that's the number I'm using in my calculation, 0.08 and times 1 minus 0.08. And I want to see if this is greater than or equal to 10. And yes, it is. So I could say yes, normal. Like that. When you're doing this step, I really like to see where you're plugging the numbers in because I want to make sure you're plugging in the true center of the curve because it's very easy to want to use P hat, which is 0.045 in this situation. I want you to use P naught, that's the center of my curve. That's all the things I calculate. Standard error and normality is from the center of the curve all the time. All right, let's take a look at our result step. Remember, this one's a little bit longer step. Hopefully we're getting used to it. I was really impressed with all the work last week. So my result step, since this is categorical, I have a z-test statistic. And remember the z-test statistic. This is my sample proportion, P hat, minus the center of my curve, P naught, divided by the standard error. Well, the standard error is the square root of, remember the center, P naught times 1 minus P naught, and that's divided by N. So I'm just going to plug all my values in. So P hat is 0.045. We just calculated that up here above. Minus the center of my curve, which is 0.08, divided by the standard error. So it's 0.08 times 1 minus 0.08. That's divided by N, and that's all under the square root, or sorry, 200, and that's all divided by, or under the square root. So here I get this value, which is negative 1.8245. And that's my test statistic. So I'm going to interpret that. I'm just going to say my P hat is 1.8245, standard errors below the center of 0.08. I don't need to include the negative in front of my 1.8 here because I'm saying below. Below is indicating it's negative. If I said above, that'd be indicating this is positive. So I always write the number here as a positive, and then below means negative, above means positive. All right, so let's look at the p-value and calculate that. So before I actually do anything here, I need to look at a drawing so I can get a feel of what's going on. So here's my curve. Remember, we're on the Z curve over here. So the center is 0, and I'm going to put my test statistic on. So negative 1.8245. I'm going to be calculating this area and this tail. It's always the area and the tail. So here for my p-value, I'm going to calculate the probability that another z value is less than negative 1.8245. So I'm going to do this by plugging this into my normal CDF function in my calculator or Minitab. I'm starting at negative infinity, which you know in my calculator, it's going to be negative 10,000, and I'm going to work my way up to that negative 1.8245. Then I need to enter in my center of 0 and my spread of 1 for my z-curve. When I do this, I actually get a p-value. So let me just write that here. My p-value is the probability this area under the curve is going to be equal to 0.034. I think I went out even further. 0.04, like that. So this area right here is 0.03404. That's the area in this tail. But I need to think about what I have. I have this problem where it says it's different. It's not equals right here. Not equals in my HA. That actually means that my picture looks like this. It means it's a two-tailed test. So if it's a two-tailed test, then I need to make sure I account for both tails, the area in both, the area under the curve for both to get the probability for both. This is symmetric. When I have a not equals, it's always centered. So what happens here is when I'm using a normal CDF function here for categorical, or if you're using the T-CDF for numerical, you're only calculating what you're giving it, which is the area over here on this left. So that's only the 0.034, but I need to accommodate for this and account for this area on the right as well. So I need to multiply this number by 2. So I can get the total area. So my p-value is actually 0.068. You can round it up to 1. Excuse me. So now I have this total p-value. So this is the p-value. So we thought the first number was the p-value, but it was really just the area, and then I need to get the true p-value, I need to multiply it by 2. Okay. All right, so I'm going to interpret this, and then I'll show you my calculator function. So I'm going to say if the population proportion is equal to that 8%, I'm just going to leave it as 0.08. There is a p-value, which is 0.0681 probability that a proportion, or that we get a sample proportion at least as extreme as the other one. I don't know if I want to say that, let's see, that we get a sample proportion at least as extreme as the one we got from sampling. Okay, so there's my full results step. I'm going to grab my calculator. I'm going to show you this. So I'm looking at my calculator here. So I'm trying to get the, okay. I'm going to hit stat right here. So I'm going to press stat. And see how you can arrow over and it says test is the one on the right. I'm going to go to test, and if it was numerical, I would do the second option, which is t-test, but this is categorical, so I'm going to use the fifth option, which says one proportion z-test. So I can choose that option. What this does is this gives me both test statistic and p-value all at once without doing all of the work myself. So P naught, this is the center of my curve. This is the 0.08. X is the number of individuals with the characteristic that we're studying, which is 9. N is my sample size, 200. And then the next one is my HA. So it's whatever I choose for my HA. And you can see that first option right here is a not equals. So we're saying it's not equal to P naught, which is 0.08. And I'm going to calculate it. By choosing that not equals, you're telling it it's a two-tailed test, and it's going to multiply that p-value automatically for you. So you can see here we get a negative 1.8245 for my Z test statistic, and then look at the p-value right below it, 0.068. Right there it is. That's the p-value that's already multiplied by 2. It accounts for both tails. So you only need to multiply by 2 if you're using your CDF function and calculating this yourself. Doesn't matter which way you use. For me, they're not really that big of a difference, you know, in a time savings. So just choose whichever way and then know if you have to multiply by 2 or not. Okay, let's take a look at the conclusion step. So this is a quick step. So for my conclusion step, I'm going to ask myself, is the p-value less than or equal to alpha? So my p-value is 0.068. And I want to know, is that less than or equal to 0.05? Right? So the answer is no, it's not less. So therefore, we cannot reject the null hypothesis. So now I want to write a conclusion statement. The conclusion statement includes my level of significance, if our sample supports the goal or not, and then I restate the goal. So at the 5% level of significance, our sample, now since we said no, cannot, which these are all negatives, right? No and cannot. I'm going to stick with the negatives and say our sample does not show, and now I'm going to go right back to my population step, and I will take my goal and I'm going to copy and paste it right into here. It does not show support to say that the population, it's always about the population, proportion of Asian men who are red-green colorblind is different than the 8%. So there's my conclusion statement. So I really don't have to do a lot of work from here. This is the work, right? And then this one is all copying and pasting, just adding in the 5% level of significance, and that my sample does not show support. So let me just underline this. So we get it, no, cannot, does not. If I did, it would say yes, can, does. All right, so what we're saying here, that we cannot reject the null, then that means we cannot state that the population proportion is different than 8%. We're saying it probably is 8%, right? We cannot say that it's not. Our sample does not give us evidence to say that it's different than 8%, so it probably is. That's what it means when I cannot reject my null.